Morning, Alexis. Morning, Kayla. Okay, so good morning, everyone. I hope everybody had a great weekend. Hope you did well on the test. I have not looked at those yet. I will start grading your portfolios soon, but just, a little heads up for me personally, I'm going through a week where I'm defending my dissertation orally. Then I'm going to the institutional review board with it. So it is a super crazy, hectic week for me, but I will get to those way before the grades are due because, as you know, this class is coming to an end. We have 3 sections left. We're going to cover 2 of them this week, 4.1 and 4.2. The last section in the book is section 4.7. And so we'll do that next week, as well as the review for the final. So we are totally wrapping this thing up, sliding into when we're going to take that final exam. You will be taking the final exam on honor lock. So just a heads up, I've reminded you of this before, but I'll mention it again. That honor lock is a system that we pay, the college pays for. They'll ask you for an ID. You have to have a workspace that you can show them, a desk that is dedicated just to taking the final exam, no papers other than I will let them know that you can have 4 3x5 index cards on your desk and a calculator. when taking the exam, and that you can have scrap paper, but they're only going to let you have one piece of paper at a time. When taking the exam, they'll do a 360-degree view of your room several times during the exam, and you can't have anyone else in the room when taking the exam. So just things to think about so that nothing is a surprise. You don't need that kind of anxiety on exam day. Everybody seems to be doing pretty well. I mean, there's some people that have just, floated away into space and have their own issues going on. I know it's a tough time for everybody, but in general, the great majority of the class is doing quite well. So I'm very happy about that, and I'm sure you are too. And we're going to continue now with section 4.1, unless anybody has any questions for me. Okay, the other thing that I want to, but feel free to jump in, that I want to mention is today I am going to have to, this is the only time I've done it during the whole semester, but I do have to cancel my office hours. I had a couple of office hours scheduled today, but my oral defense for my dissertation interferes with that, and I have no power over when that is scheduled. So for today, I'll have to do that, but I will kick right back in with my office hours tomorrow and Thursday. And then, of course, I was available yesterday. So feel free to get together with me if you have anything that you need to discuss. Just know in general that a typical question asked at this time is, how can I improve my grade? There's not a whole lot that's left because there's only certain things that I'm allowed to do. And I cannot open up the assignments because you guys are in an ELE, an adaptive learning section of ALEX. Those assignments cannot be reopened because then it impacts everybody's, the due dates on everybody's PI objectives. So that can't be done. No tests are allowed to be retaken when you're taking any kind of a college course, because then you are given an unfair advantage that other students don't have, and we're all about equity here. So that can't be done either. So put your sights not forward. If you're wondering what can you do to improve your grade, don't let yourself have any zeros. I mean, having zeros on the one thing that you can control, which was the portfolios, that would not be advisable. There were many portfolios assigned, and allowing zeros to be input for those scores is going to drag your grade down when I go to do the final averages. So you can still do them if you did, if there was a couple of them that you let slip by. It's just that, it would be 30% off for it being late, but it's better than getting a zero. And the other thing is the final. The final counts more than your actual individual test do, slightly more. I believe they're at 20% for the final. But again, this time it's not unproctored. It's going to be proctored by a professional proctoring service. So just keep all those things in mind and let me know if there's anything that I didn't mention. Got a lot going on in my head this morning. Okay, so we are going to go to 4.1. I'm going to do the lessons note packet. There's only 2 pages dedicated to section 4.1. A lot of it's terminology. So I'm going to get most of my examples regarding actual example problems from the book. So I'll be using from the book, page 458 to 461. So I'm going to start first with the terminology. Let me change over to document camera. Okay, let me try and get this straight. Okay, here we go. Okay. All right, so the first thing I wanted to try and do is give you a little background on the different types of reasoning that you're going to be expected to do in this chapter. We're going to be looking at inductive reasoning as well as deductive reasoning, and I want to try and start off by giving you an example. Of course, I'm going to be giving you many numeric type examples, but I'll start off with just a layman's type of example. So here's a scenario. A tourist who visited Key West met a number of people from the Keys who were all relaxed and laid back. The tourist concluded that all people living in Key West were relaxed and laid back. This conclusion was reached by what we call inductive reasoning. And I'm going to explain to you what inductive reasoning. It says it right here. It is a powerful method for drawing conclusions. However, it is not based on fact. Whereas deductive reasoning is, because they're going to really ask you to be able to tell the difference between inductive and deductive reasoning. It is not 100% true. In fact, you can prove that any conclusion that's been drawn by inductive reasoning can be disproven by way of what we call a counterexample. If you can come up with an example that proves that the conclusion that the person came up with is wrong, then that means that it is not 100% true. It is not a fact. So, for instance, and I think they give it to you right here. So let's just continue and you'll see what a counterexample is. The conclusion one reaches through inductive reasoning is it's not actually called a conclusion. It has the special name of conjecture. This is the name we give to a conclusion that can be proven false. It's also called a hypothesis, and you may have heard this phrase before. It can also be called an educated guess. This person is assuming that all people in the Keys are relaxed and laid back, but only because he saw some very specific examples of people walking by. Who knows what's going to be on the next block if you continue walking? You may see people that are acting crazy and irate and angry. Okay, so a conjecture from the last example, it's an assumption that people might make from what they're observing. All Key West residents are laid back just because they saw a few cases of it. If there's just one case, hold on. If there's just one case that disproves the conjecture, it is known as a counterexample. Any case that you can come up with that disproves this assumption that the person made that all people are laid back, that's what we refer to as a counterexample. Okay, a counterexample from the last example would be something that I already verbally said. One Key West resident that is stressed out. All you have to do is find a person who is acting very stressed out, and that disproves this assumption that this person made, also known as a conjecture, hypothesis, or educated guess. On the other hand, as opposed to inductive reasoning, we have what's called deductive reasoning. And it's the kind of reasoning that we use in many math classes. But I'm going to say, the kind of deductive reasoning is more when you take a course in logic. That would be like, a higher level math class, maybe at university level. We do have some of that here. But those are, people that are kind of majoring in math. They will take courses in logic, and they will do a lot of this, where everything that they do a lot of what's called establishing a proof. And they have to use reasons in their proof when they're doing deductive reasoning that are known to be true facts. So when you're reasoning through deductive reasoning, It's the process of proving a specific conclusion. You're trying to prove a specific conclusion from one or more true statements, which are also called, I'm going to give you its other name here, true statements are called premises. Or we can call them just true statements. They are statements that are generally accepted by the population as being true. They've been tried over and over again and have been proven to be true. So we use those to try and reach the conclusion that we are trying to prove. A conclusion that is proved true by deductive reasoning is actually called a conclusion rather than a conjecture. So a conclusion is called a conjecture when you're doing inductive reasoning. You're just making assumptions. And it's called an actual conclusion when you're doing deductive reasoning. So here's an example of deductive reasoning. Okay, it says the syllabus states that any final average between 80 and 90% will result in a B. If I get 78% on my final, my overall average will be 80.1%. That means I'll get a B. Well, according to your syllabus, that is true. I don't put things in the syllabus that aren't actually things that we're going to abide by. So they're taken as true statements that you can count, which is this scenario that you're seeing right here. Okay, so this is an example of deductive reasoning. Okay, now this table down here at the bottom is just kind of a summary of what I've gone over thus far. I'm also going to give you examples of both cases. And I want you to know that, what I would hook on to here in this deductive reasoning definition is that the conclusion is based on some general rule that is accepted as being true. And that is, yours would be your syllabus. There are rules put into that syllabus that we abide by. They are accepted as being true because the teacher has told you that you're going to abide by those rules. All right, so to summarize what we've done so far. Inductive reasoning, what are the uses? I think I'm going to start this over here just so I don't run out of room. To make an educated guess based on specific examples or patterns that you happen to be observing. The conclusion is called a conjecture. Can the conclusion be disproved? Yes. And that would be by providing a counterexample. Whereas with deductive reasoning, which is all this information, the reason, the uses of deductive reasoning is to prove. You cannot prove something is true when you're doing inductive reasoning because you're only making what's called an educated guess based on some very specific examples that you have observed. But with deductive reasoning, you can actually prove that something is true because you're only using true statements as your reasons for why it's true. To prove that a conclusion is absolutely true. Although I use that word loosely, I don't know if anything is absolutely true. There's too much in the unknown. What is the conclusion called? A conclusion. Or a fact. You could call it a fact. Can the conclusion be disproved? No, because in your journey in trying to prove that something is true, you're using only true statements as the reasons to support your proof. So when your conclusion is based on nothing but truth, then we take that conclusion to be a fact that cannot be disproved. That's what a fact is, something that can't be disproved. Whereas an assumption can be disproved by providing a counterexample. Okay, let's go to the next page. Let me see what we have there because we might have to go to the book depending on what kind of examples are here. Yeah, I want to save this for the end. So we're going to go into the book now. I am going to be using page 458. And a lot of what you're doing in Alex and in the book is more along the lines of inductive reasoning, where you're observing patterns and trying to make an educated guess as to what the next number is going to be in the pattern that you're seeing. So for instance, let's look at what we have here. This is what we call, I didn't copy page 457 because it was just a group of a bunch of judges in a courtroom. But you could be talking about anything. Let's say you're just talking about people that are at a party or at some kind of gathering, and you're trying to determine how many handshakes, unique handshakes. No one's allowed to shake hands with the same person. Not that we're shaking hands right now with all this going on, but let's just say this is actually called the handshake problem. And let's say you have 3 people in the room and you want to know how many unique handshakes can occur in that particular room when there's 3 people. How many handshakes can occur if there's 4 people in the room? So the dots represent the people. So here there's 3 people. Here there's 4 people. Here there's 5 people. And what you're going to do for this handshake problem, which is a classic inductive reasoning problem, is you're going to start off by drawing the handshakes using line segments. And then because the drawings are going to get quite complicated, there's just going to be too many lines that are crisscrossing, so it'll make it super hard to count up the lines. You're going to then move over to your ability to reason inductively. Then you're going to switch over to looking at what is the pattern that is evolving in the numbers that you see, the number of handshakes. Okay, so let me demonstrate for you. When you have 3 people, now remember, you cannot draw the same line twice because that would be the same 2 people handshaking twice, and that's not allowed. So you could let these 2 people handshake, these 2 people handshake, these 2 people handshake. Pretty easy because there's only 3 people in the room. So off of this, we got 3 handshakes. Okay. Then let's move to the next one. And you'll see that, there just starts to be more lines because you can draw more diagonals through the center of the figure. I'm going to do the most obvious handshakes first. So there's 1, 2, 3, 4 handshakes. And then you can let these 2 people handshake, and you can let these 2 people handshake. So here there were 6 handshakes. If it starts to get complicated because the number of people have increased in the room, then I'll keep track of how many handshakes there are off to the side. Okay, here I have 5 people in the room. So here there's 1 handshake, 2 handshakes, 3, 4, 5. And then let's see if we can get this right. So far I have 5 handshakes. Okay, now I'm going to go start on any point you want. I guess I'll start right here. And try to go to as many other places as you possibly can. Try to handshake with as many other people as you can that you haven't already handshaked with. This person has already handshaked with this person and that person because you can see the segments are drawn already. But they could handshake with this person or this person. That hasn't been drawn yet. So I just got 2 additional handshakes from this location. Now I'm going to go over here. Let's see, make sure we couldn't go anywhere else. Went there, went there, went there. There's nowhere else for us to go. Okay, so now let's stand right here and see if there's any other place we can go other than where we've already shaken hands. We went that way now. So we could go straight across and we can go right there. Okay, so from this location, I just got another 2 handshakes and I'm done there. Now let's go to this position. Right here, let's see, I've already handshaked with this guy, I've handshaked with that guy, already handshaked with this person, but I could go here. Here's a line that hasn't been drawn yet. So I got 1 additional handshake off of that location. You're going to see that the last 2 positions, there won't be any new handshakes that you can conduct that haven't already been conducted. So look, see from this position right here, even though you try, you've already handshake there, you've jumped across, you've jumped over there, nothing new. Likewise right here, there are no new handshakes. So the total number of handshakes for this situation with 5 people in the room would be 7, 9, 10. 10 total handshakes. Now we're going to use these numbers because, again, we're already getting into a situation where the drawing is getting, kind of complicated, and it's more so here. So we're going to stop drawing after we get done with the case where there's 6 people in the room, and then we're going to break off into trying to see what the patterns are. Okay, so here's 1, 2, oops, missed, 3, 4, 5, 6. Those would be the most obvious handshakes. I'll keep track of them here. And then start wherever you want. I'm going to start right here. And I'm going to try to travel to places that I haven't done handshakes with yet. Okay, so let's see. I could go there. Count them up as you go along. Got an extra 1, got an extra, I'm up to 2, 3. So I got 3 extra handshakes there. Okay, so I'm done there. Now let's move right here. So this time, let's see, where else can I go that I haven't already gone? Because I've already handshaked with that person and I already handshaked with that person. But I have not handshaked this person over here. I haven't handshaked with this person over here. And I haven't handshaked with that person. Not from this location anyway. So that just gave me an additional 3 handshakes. Okay, now let's move to this position to see if we can get any brand new handshakes. So I've already gone there and there, already gone there, but I could go across. I could go straight across. That would be an extra 1. And I could go straight down. That would be an extra 1. So that would be 2 additional handshakes. Now moving to this location, see if there's anything new I can get here. I've gone there and there. I've gone to that. I've gone to that. Let's see, I've gone to that one. I've gone to that one. But I haven't gone here. So I could draw that line right there. So there's an additional handshake at that location. Now moving here, once I get to this location, I've gone this way, I've gone there, I've gone there, I've gone there. There's no extra ones here. And if you go here, once you stop having the ability to have extra brand new handshakes that you haven't already done, that means the last one's not going to have it either. Okay, so altogether I had 9, 12, 14, 15 handshakes here. And these numbers that I just got off the pictures, they're going to help me to fill out the table. Okay, so that's what you see down below here. So again, a lot of these inductive reasoning problems, they start off a drawing, and then you're going to continue to get answers that are further into the future. Like, what if somebody was to ask you, what happens when you have 9 people in the room, which is being asked in this table, but yet the drawing is too hard to do. It just gets too confusing, and typically you lose a handshake too and get the whole answer wrong. So we're going to use this table, and then we're going to look for patterns in the table so that we can actually answer what if 9 people were in the room. They're calling them justices because they're calling the people, they were judges that were in a courtroom. Okay, so if there's 2 people in the room, all you can do is one handshake between the 2 of them. After that, they'd be handshaking twice. 3 people, we just did a picture for it up here. There were 3 handshakes. 4 people, there were 6 handshakes. When there were 5 people in the room, there ended up being 10 handshakes. When there were 6 people in the room, there ended up being 15 handshakes. And I don't have any more pictures after that, but I can look at patterns. Like when we were in the last chapter, we were noticing that as we came down this column, that it would be the same incremental jump as we passed from number to number. And also when you came over here, which is why the picture ended up being a straight line in the last chapter, it will be the same incremental jump here. That's not going to be the case here. I mean, here I know it's jumping by 1, 1, 1. But here, look what's happening. Here you're jumping in an increment of 2. To get from 1 to 3, you'd have to add 2. Then as you jump from this number to this number, you're jumping by 3. To get from 3 to 6 is an increment of 3. Then as you jump from 6 to 10, that's an increment of 4. As you jump from 10 to 15, that's an increment of 5. So I'm sure you can see the pattern that's happening there. Each time the incremental jump is one number bigger. So therefore, following that pattern is where you're doing inductive reasoning. You're looking at a pattern and being able to get the next 3 answers. So this will be, from here to here will be an incremental jump of 6, giving you 21. From here to here will be an incremental jump of 7, giving you 28. And from here to here will be an incremental jump of 1 bigger, because each one of these is 1 bigger, giving you 36 handshakes for 9 people. And you could go as far as you want. It's just that it's not, doesn't make sense to try and do drawings because they look how complicated, look how many intersecting lines we already had just at the case when we had 6 people. Okay, so that is an example, the handshake problem. And there are many types of math problems that stem off of this handshake problem. Let's go to the next page and see what else is there. Okay, so now these are some inductive reasoning problems that are more like in the form of a problem scenario rather than a numeric table that we're filling out. So these will be worded type answers. So it says you make an educated guess. You made an educated guess about the number of handshakes necessary for 9 justices using inductive reasoning. Conjecture is another name for an educated guess, which we went over already in the lessons note packet, the terminology and names that we use. Proving that a conjecture is true almost always involves inductive reasoning. For example, watching a couple of races on TV, you might conjecture that all NASCAR drivers are men. But that would be because you only saw specific cases where they were men and didn't give yourself enough time to see that there are more than just men in that particular type of sport. So in order to prove that conjecture, you would need to confirm the sex of every single driver in NASCAR. Just watching a bunch of races won't prove anything. So proving that a conjecture is false is much easier. You need to just come up with a single example that violates the conjecture, also known as a counterexample. You're just coming up with something that proves the assumption that someone's made. So for instance, find a counterexample to prove that each conjecture, to prove that each assumption is false. So this says every time it rains. Now you could have different answers here. There are different things that you could come up with to disprove inductive reasoning. So it says every time it rains, my softball game gets canceled. Our game was canceled last night. So somebody comes up with this conclusion, this conjecture. They're assuming, well, if the game got canceled last night, and we know that every time it rains, the softball game gets canceled, then it must have rained last night. But if any of you have played ball before on any kind of a team, you know that games get canceled for several reasons. And I'm sure you could come up with many reasons, but just a couple of examples might be as a counterexample. Counterexample would be a reason other than what's being conjectured here that would serve as a reason why the game got canceled. So maybe the ump did not show up. That would be a reason for a game getting canceled. Maybe there were not enough players. There's an established number of players when you're playing organized sports. Oops. Let me squeeze the word not in there. There were not enough players. So anything like that, like I said, your answers can be different. One student might give this a reason, one student might give this as a reason, and there's a multitude of reasons that could be valid counterexamples. Sometimes you're going to be doing numeric type problems and coming up with a counterexample that has to do with more of a numeric problem. So, such as the one that you're seeing here. Here's an equation. This is what we call an equation in factored form. Factors are things that you multiply together to get the answer. So you see how it's this quantity times this quantity times this quantity. Those are called factors. And inside, and the factors are actually expressions. They're variable, algebraic expressions. So in part A, it says, substitute -3 for x and find the corresponding value for y. Okay, so let's see. I'm going to put the 3 parentheses. If I'm going to substitute for x, that means I should leave a blank spot for each of these x's, but I can copy the rest of it. 2 times x minus 1. Okay, and so then let's see. I'm putting in a -3, so this will be -3, -3, -3. And some of you may see the answer already. If any of these factors are 0, it makes the entire thing equal to 0. But I will put the numbers down there. I will show you my work just so you can verify it in a calculator if you want to. Okay, in the first factor, for this first factor, plugging in that -3 gives me a 0. So there's a 0 in there. Then here is -10. And then negative 2, 2 times negative 3, let me make that a little clearer. Would be negative 6, take away 1, so negative 7. And when multiplying, if any of your multipliers, also known as factors, is 0, then the entire product, that's the answer you get when you're multiplying, the entire product is 0. Okay, it says repeat this experiment for x equal to 7. So if you went and did it again, it would be x plus 3. It would be x minus 7. And in the third parenthesis, there was 2 times x minus 1. This time it said put in a 7. And you can see that this time they are causing you to get a 0 in the middle. So again, justifying the fact that if any of these factors, any of these multipliers are 0, the product is 0. Okay? And you can put that in your calculator to verify it. You could toss those into your calculator. This would be 14 minus 1, but really who cares what the other numbers are? It's just because if this is 0, this is going to be 0. Okay, so someone comes up with the conjecture after seeing this. You were told to plug in negative 3, and you got an answer of 0. You were told to plug in 7, and you got an answer of 0. So along comes somebody, and this person says, well, it must be true that anything you plug in is going to result in a 0, because they saw these two specific cases. They just assumed, which is what a conjecture is, that any number substituted in for x is 0, and you're trying to come up with a counterexample. So a counterexample would be for you to use any number other than a number that causes a 0, because you have specifically been led to use a number that they knew would cause this part to 0 out. Then you were led into using a number that would make this part 0. And you could tell, just using the number that's the opposite of this is going to make it 0 out. Using the number that's the opposite of that, positive 7, will make that 0 out. This one's not so easy to see just by looking at it, but it is a 1/2. 2 times 1/2 is 1. And then 1 minus 1. So just use anything other than the 1/2. You could already see what the negative 3 and the negative 7 did. So here's a counterexample. If x is, let's say, 2, anything other than the thing that do make it 0, because you're trying to prove, hey, there are numbers that you could plug in that don't make it 0, and you could even show your work, show why this is actually a counterexample. If x is equal to 2, it is not true that y is equal to 0. In fact, it isn't equal to 0, and then you could show why that's true. In the first parenthesis, it's x minus 3. In the second parenthesis, it's x, and we're using this, x plus 7. Oops, got that backwards. It's supposed to be x plus 3 and x minus 7, and then 2 times x minus 1. And I'm using a 2. So you see that this time I haven't created a 0 in any of these parentheses. So therefore, I have just come up with an example that when I plug in 2, it does not, in fact, end up being 0 when multiplied. That 4 minus 1 is 3. And you can see that you get negative 75 there. So that would be your complete proof that you just found a counterexample. Come up with something that disproves it, and if it's a numerical type of problem rather than the one that we saw up here, where you can't really show any work, you can only just explain your answer in verbal form. But if it's a numeric type of problem, you could actually show why it contradicts the conjecture that was made. Okay, so does anybody have any questions for me thus far? Okay, I'm going to do this one right here. Let me see if there's anything on the other page. Yeah, there's stuff on the other page as well that I want to go over with you because you're probably going to see it in Alex, so I do want to go over it. But I don't want to skip this one right here because you don't have enough of a geometry background and you're going to be hit with that quite a bit when you go into the next class. By the way, please don't forget registration is open. You can register for your spring classes. You don't have to pay right away, but you can lock in a seat for the spring term. So I would get in there and try to register for the next class that you're going to go into, which should be MGF 2106 or MGF 2107. Either one of those. I mean, I suggest 2106. I just think it's a real nice follow-up to this because many of the topics are the same as what we covered in here. And so it'll be a nice smooth transition for you, whereas, 2107, it's a little bit different. All righty, here we go. So there are these three right triangles. They say that all of them, they're telling you that these are three right triangles. You know what a right triangle is? Has a little 90-degree angle. Okay? And they're telling you that they're isosceles. If you don't know what that means two equal sides. Let me tell you a little bit of background regarding right triangles. In a right triangle, we always have what's called the hypotenuse. These are called the legs, and you should be familiar with that because you're going to be asked to use the Pythagorean Theorem. So what the Pythagorean Theorem states is, so again, the legs are the two pieces that connect at the right angle. The hypotenuse is the slanted side across from the right angle, and it is always the longest side. So therefore, when somebody talks to you about having an isosceles triangle, that means that there are two sides that are equal. But it cannot be the hypotenuse because the hypotenuse is always longer than the legs. So it has to be the legs that are equal. Okay, just a little bit of something that you should know about. So in this one, it would be these two pieces because those would have to be the legs and that slanted side would be the hypotenuse. Here it would be these are equal and this would be the hypotenuse. So there is a theorem called the Pythagorean Theorem, and I'm going to use that theorem to give my conjecture. Here's the conjecture. This is the assumption that someone has made based on this given information that you have three right triangles and that they are, each one of them are isosceles with two equal legs. So somebody says, well, it must be true that every right triangle is isosceles. And in fact, that's not true. First of all, in order for you even to deal with a problem like this, you would have to know that all right triangles obey the Pythagorean theorem. If the numbers that you're being given for the sides, like somebody's going to tell you the length of this side, the length of this side, and the length of that side. If the numbers truly belong to a right triangle, then they will obey the Pythagorean theorem, which goes like this. Hypotenuse squared, keep the hypotenuse on one side all by itself because this is an equation, the Pythagorean theorem. And then over here would be the legs. Legs squared plus legs squared. So I happen to know my Pythagorean triples, obviously, because I'm teaching it all the time. And one of them is the 6, 8, 10 pair. This happens to be what we call a Pythagorean triple. 6, 8, 10. In other words, you could have this leg 6. Remember, the hypotenuse has to be the biggest side. Maybe this one will be the 8. And this will be my hypotenuse. So I could say, okay, well, here's my counterexample. I happen to know of a right triangle that has legs 6 and 8, and a hypotenuse of 10. Hypotenuse has to be the biggest side. I can now prove that my counterexample works, or justify it. Let me use that word. I don't want to use such a strong word. I can justify that this actually is, these are the numbers that belong to a right triangle by showing that they obey the Pythagorean Theorem. Okay, so I'm going to put it right into this formula right here. Hypotenuse squared is equal to leg squared plus leg squared. It doesn't matter which of the legs you write first. Now, if this truly is a right triangle, I should get the same number on both sides, and I do. This is 100. This is 36. This is 64. Therefore, I have 100 here and 100 here. That means that these numbers do belong to a right triangle, because only the three sides of triangle that obey Pythagorean theorem are considered a right triangle. So not only have I given a right triangle, but I've also shown that not all right triangles are isosceles. This is not isosceles. Therefore, it serves as what we call a counterexample. Okay, so I gave you a verbal type of problem, verbal scenario, where we came up with a counterexample. Then I gave you a numerical problem where we came up with a counterexample, like an algebraic type problem. And then I gave you a geometry problem where we came up with a counterexample. All of those types of problems would be fair game for inductive reasoning. Okay, here would be a classic problem too. These problems called the triangular numbers. If you wanted to continue this would be a nice problem to be asked on a test or an ALEX or something like that. If you want to continue with these pictures and somebody says, find the 5th and the 6th triangular numbers. In other words, they want that number that's underneath there. So let's see. The first triangular numbers, so this is for 1 dot, 3 dot, 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You see, that's what they're counting up. So what you have to do is just look at how are they coming up with these drawings? This is a visual thing. So like when you're going from, you can't tell much from, I mean, you can tell from here to here. I can describe to you how they developed this with respect to this. All they did is they went up this direction by 1 point and then down by the same number of points, and then made sure that all the sides were closed. So to go from 1 point to 3 points, they went up this direction and drew an additional point, and then went down in the opposite direction and drew an additional point. Likewise right here, this was built off of this. All they did is they sat right here on the small one. They went up to the right. You know, this segment right here climbs upward and to the right. So going in that direction, they just added an additional point, and then they went down. And they made sure that, see how this side right here that I just drew, when I drew an additional point, there are 3 points on that side. So they made sure that as they came down in the opposite direction, that there were also 3 points. And then they closed it up. And that's how they went from 3 to 6. See? 1, 2, 3, 4, 5, 6. Okay. And then likewise, they built this big one from this one. They just added an additional point here. And then so this would constitute this side that you're seeing right here that has the 4 dots on it. And then they came down this side, making sure that there's the same number of points. So there was 1, 2, 3, 4 points coming up here. See how this side also has 4 points? 2, 3, just like that. And then they close it up. So they build each triangle from the triangle before it. So, not that you have to continue drawing them. I just wanted you to see where they came from. But at this point, instead of continuing to draw them, since you know that these drawings are getting a little bit more difficult, what you could do is you could just observe the pattern of the numbers in order to get the 5th and the 6th triangular numbers. These are the triangular numbers. 1, 3, 6, 10. Hey, we want to get the next two without drawing the picture, just like we did in the previous pages. So if you're going from here to here, let's notice how much of a jump there is. There's a jump for 2, and you're going to find this, very similar to the handshake problem. I'm talking about the incremental jumps between numbers. If you go from here to here, then there's a jump of 3. If you go from here to here, there's a jump of 4. And in observing that pattern, you realize that these jumps are just getting one bigger each time, just like in the handshake problem. So if you want to come up with the 5th and 6th triangular numbers, which is what you're being asked for, again, these are triangular numbers, 1, 3, 6, 10. But by observing the incremental jump between them, I'm able to come up with these two answers. So the next one would be, let's see, from here to here would be an incremental jump of 5, making this triangular number 15. From here to here would be an incremental jump of 6, making this 21. Okay, I don't think it would be fair to go on with this without talking about Pascal's triangle. So I just want to tell you that Pascal's triangle is used in every math class at your level, pre-calculus, it's used in trig, it's used in calculus. There are many different applications, and the kind of applications you use are based on what level of math you're at. You guys are just studying. You're just trying to get familiarized with patterns. And inside of the Pascal's triangle, there are many, many patterns. It's just that they have quite a bit of application to science and all kinds of fields, these patterns. So right now, I just want to familiarize you with this. Some of these patterns are very, very obvious. As you're going down this side, notice that it's all ones. That allows you to fill that in. Notice that as you're going down the opposite side, it's the same. And that is true of this entire Pascal's triangle. It is symmetric. You split it right down the middle. What's happening over here is the same thing as what's happening over here, which also allows you to fill them in. Notice that as we go from this outer row or this outer string of numbers and we move one in, that we have a different pattern. Here it was a pattern of all ones. Here it's a pattern of 1, then 2, 3, then 4. They're all jumping in an increment of 1. And know that this string of numbers is the same thing as this string of numbers. Because again, when you split this Pascal's triangle down the middle, you got the same stuff happening over here as is happening over here. So this would be 5 and 6, just like this was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Then let's see, as we go this way, here we're jumping 2, then 3. This is like the handshake problem. This string of numbers is like the handshake problem. You're jumping 2, then jumping 3, then jumping 4, then jumping 5, and whatever this string of numbers is doing, this string of numbers is doing. So if this was 1, 3, 6, 10, 15, then this is 1, 3, 6, 10, 15. Usually the only one that students really question is how to fill this one in. But if you notice, you probably maybe didn't notice this yet, but any of these numbers, any number in this Pascal's triangle, if you're standing on a particular location and you just look directly to the right and directly to the left, and you add those two numbers, just look up and to the right, up and to the left, and add the two numbers, and you'll see that that's how you get any entry in this table. Okay, I'll prove it to you. Here's 4, right? If you're standing on 4, look up and to the right, up and to the left. If you were to add those two, you would get 4. If you're standing right here, look up to the right, up to the left, add those two numbers, you get 10. And that works for any entry. But that would take more time if you were doing each and every entry like that, rather than observing the patterns that are occurring in each of the different strings. Each of these strings has a different pattern. But if there's one particular cell that you're trying to fill in, then you can do it that way. Okay, I had one more page that I wanted to do in the lessons note packet, but I believe I'm going to, let's see, I'll just do one of them. Just to get you started. So if you see something like this in Alex, you're supposed to do each one of these things one at a time, and then build to the general case. So like for instance, and then I will do the rest of these. I mean, because there's like a few examples here. You do it for a 3, do it for a 4, do it for a 2, but the steps are the same regardless of which of these numbers you use. And then there's also a problem where you do it with a variable. So the first number is 3. I'm going to show you all my steps right here. Start with 3. It says add 2. Each time you do something, you want to take the answer that you just got and start all over with that number, but do the next step. Triple. Triple means multiply by 3. Get a 15. Okay, we just got 15. Now start with a 15, but do the next step. Subtract 3. Okay, you're done with the 12. Take that 12 and start next step. Divide by 3. And we got a 4. And then subtract the original number. So we just got an answer of 4. Let's continue with 4, but do the next step. Subtract the original number, which was 3. And you're going to see that no matter which of these numbers you use, if you use these particular set of steps, you're always going to get a 1. You can, and therefore you can generalize this particular scenario using an algebraic expression, and that is what part B is about. Okay, this time it says let the original number be a variable rather than a number like what I started with here, but you do it in the same way. So you would start with whatever they gave you, n, and you're going to do one step at a time. Add 2, triple the result. Each time using the answer that you got to do the next step. So the first step is add 2. Okay, so that's my step that I just did. Now I'm going to triple the result. I had a result of n plus 2, and if I'm going to triple something that involves 2 terms, I need a parenthesis around that expression. Okay, this was step 1 from adding 2. I took the n plus 2 down here, tripled it. That gives me 3n plus 6. Remember, distributive property means multiply by that multiplier out front, using it on each of these terms. That gave me 3n plus 6. Just like I did the problem up here, whatever you get for an answer, start with that answer, do the next step. So I already did the add 2, I already did the tripling, now I'm going to subtract 3. My answer would then be 3n plus 3, because 6 take away 3 is positive 3. Okay, I got an answer of 3n plus 3. Start again with that answer and do the next step, which is divide by 3. You're dividing all of this by 3. And by the way, when you're dividing an expression that has 2 terms, both of them get divided by 3. So it's 3n divided by 3 plus 3 divided by 3, which is, let's see, the 3's cancel and you end up with just n. And then 3 divided by 3 is 1. So my answer here was n plus 1. Take that answer, bring it down here to start for the last step. And the last step is to subtract the original number. Well, the original number this time was n. And what do I end up with? A 1. Just like I ended up here when I used numbers, the number 3. You would have gotten the same answer, a 1. If you used a 4 and a 2. Using this set of steps, whether it's a number or an expression, results in the number 1. Okay, so that is a ton of examples. You're off and running on section 4.1. We have 2 more sections left to go, and then we'll begin reviewing the final. So everybody, I'm sorry to cut out a few minutes early, not that you're going to mind that, but like I said, I have my oral defense today, and I have to, skedaddle on to that meeting right now. So everybody have a beautiful day, and I will see you on Thursday. Bye-bye. Welcome, Aaliyah.